So guys, just as by way of giving us a reconnecting point, if you remember last time, we spent almost an hour fiddling around with these stupid things, and all of a sudden we started to learn all these interesting ideas about equilibrium. Then at the very end of the day, we came to this idea, and we talked about the idea that equilibrium truly is a constant state. And it doesn't matter what angle we come at this condition, we can start with all reactant and no product, all product and no reactant, somewhere in between. But guys, this equilibrium constant truly is a constant, as Matthew pointed out, based upon the relative K values. There's a proportion there that indicates how much of the reactants and products we'll have in these equilibrium mixtures. And it doesn't matter the direction we come at it, that will not change unless we change the values of little k, which are the rate constant from the rate laws. So guys, this is where we left off. Anything prior to this you want to talk about? You feeling okay? Okay, so guys, what we need to do then is we need to move forward, and we need to spend a little bit more time digging more deeply into these product divided by reactant ratios, which we call equilibrium expressions. So guys, this is where we're going to pick up, and we're going to talk about how we represent these things mathematically. So when we talk about equilibrium in a mathematical sense, guys, we use a ratio of products divided by reactants. Now, I don't know that you need to write this down because you learned this last time. But guys, if you remember what we did last time, we just did Kc is equal to product concentration divided by reactant concentration. But because we were simply just moving blue water around, this was simple because the process was simple. Guys, there's one more additional layer to this that you need to get straight to really be able to fully and correctly do these, and that's this. Because I don't even know if you need to write it down other than to pick up on the additional mathematical connection that happens when we write Kc expressions. Do you see it? What's new to this in blue? The exponents. So guys, the deal is this. When we write Kc expressions, we can write Kc expressions from the balanced equations. And when we do, the coefficients from the balanced equations become exponents in the Kc expression. So remember, products divided by reactants, so it's C raised to the Y power, D raised to the Z power, and then of course A to the W and B to the X. So the only thing to take away from this is to simply point out that, guys, the coefficients from the balanced equations become exponents in the Kc expressions. Is that okay? Okay, so guys, with that said then, let's dig in a little bit to what these Kc expressions are actually all about. So guys, Kc is what is termed an equilibrium constant. I know we touched on this last time, but let's be sure we're clear. Guys, there are way more K values than just Kc. Again, this year we're going to do Keq, Ka, Kb, Kw, Ksp, Kp. Ooh, there's one more. I don't even remember. Guys, there's K values all over the stinking place. And the thing that they have in common is they are always product divided by reactant ratios. For this particular one, the C simply means concentration or molarity. And guys, regardless of what it is, these things are only dependent on the stoichiometry of the reaction, not the reaction mechanism. So we can write Kc values, unlike rate laws and things like that, we write Kc expressions right from the balanced equations. It doesn't matter how reactants become products. The only thing we need to know is how much reactant and how much product is present at equilibrium. Now guys, as you're catching up with me, realize that everything that we just talked about, you should have learned last year during quarantine over a screencast. So if you have questions, let me know. Normally this is just like, oh yeah, we remember. But I frankly don't know what you remember because it was such a weird spring. Does this sit okay? Thoughts or concerns with that? You're good? You sure? Are you caught up? You're all right? Okay. So guys, with that said then, let's just invite into this conversation another K value. I don't know that you even need to write any of this down other than I just need to present this to you. So guys, at this point, we've already talked about gases. We've done Boyle's law, Charles' law, all that other stuff. Another thing that we can do with gas-based systems is we can write K expressions for them. But instead of these things being Kc, they're actually Kp. And instead of we plugging in molarities, we plug in partial pressures. So guys, P represents pressure, not concentration, and they work exactly the same. The only difference is that instead of these being molarities, they're actually the partial pressures of the gases within a mixture, but the math and everything else is exactly the same. You're just plugging in different values. You okay with that idea? Okay, so it used to be that I had to teach you how to convert KPs into KCs. They're not the same value. There used to be guys, grab your AP sheets. I think they did finally formally take it away. Is there, and we may as well look at this now. So guys, we're on the page 3 side of the equation sheet. Holy smokes, there's like 1,100 K values there. There they are, Kc, Kp, Ka, Kb, Kw. They forgot Keq and Ksp, but we'll talk more about those later. Are you beginning to get the sense that this is a big deal since it's the largest part of the equation sheet? And guys, you see Kc there, of course, and they wrote that out for you. Okay, so it is gone. There is actually a mathematical relationship that allows you to convert Kc to Kp, but you don't need to worry about it. The only thing you may need to know generically, is that trash? The only thing you may need to know generically is that they're not the same. It used to be that we had to figure out how to convert, but we don't anymore. But that's the scoop with that. Okay, so here's where we are. We've got this idea of equilibria. We've got this idea of reactants becoming products, products becoming reactants. And we now know that we can describe these systems at equilibrium by writing Kc or Kp expressions, which are products divided by reactants. You all good? Okay. So guys, with that said, and again, most of what we just talked about was kind of review from what you learned last year. Guys, now we're going to go in some interesting new directions. We've got 2 more things that we need to talk about today. Both of them are important. Both of them are new. And guys, one of them is going to be critical to your understandings for the rest of the year. Before we do, we're going to talk a little bit about what Kc means. And then guys, we're going to dig into the deep, dark recesses of this stuff and talk about some interesting things. So first of all, let's do this as a transition, and then we'll move on from there. So guys, the information contained within K, this may be worth writing down. So guys, the magnitude of K tells us all sorts of interesting stuff about what reactions are doing. But I'm thinking, given what you already understand about K, you can sort this stuff out and figure it out. So guys, what does it mean if K is large? And guys, understand, when we're talking about K values, these things, these numbers range on the order of about 10 to the 8th down to about 10 to the negative 10th. So we're talking about huge ranges in values. Very seldom do we see K values that are even in the tens or the hundreds or the thousands, or the tens, hundreds, or thousands. We're talking millions and millions or billions and billions. They tend to be really big numbers. But guys, what does it tell us about a reaction if K is huge? Lots of what? Lots of product or reactant? Uh-oh. So guys, good heavens, y'all. Does that help at all? If it's huge, you're going to get a lot of product. And guys, I know right now you're having to think through that thing and go, okay, products divided by reactant. But guys, you will very quickly just be able to knee-jerk look at these things and go, I know about what that thing's doing simply based on its K value. So guys, when we have values that are huge, that tells us that these reactions favor products. Or the equilibrium, this is the other way we say that, the equilibrium lies to the right. And then conversely, if K is small, much less than 1, but not negative. That means that the reaction favors reactants and the equilibrium lies to the left. So guys, this is worth saying as we get... That was odd. Guys, this is worth saying before we get into this. And I know you get this, but sometimes... So if you have a K value on the order of 10 to the negative fifth, I know as I say this, you're going to be like, okay, I understand that because I learned it in math. Guys, this is not a negative number, right? It's a small number, but it's not a negative number. So when we say that K is small, we're talking about things like this. Guys, why can K never be negative? Because what would that require? Negative molarities, less than none, that's impossible, or negative pressures, less than a vacuum. Guys, that's also impossible. So do you understand why K can never be negative? Because practically it just doesn't make any sense. Is that okay? Okay, so there's one other thing that you will see periodically throughout the year that we need to mention, and it's simply this. Again, I don't know if you need to write it down, but what if you switch sides? And guys, none of you have asked about this, so let's talk. So we've got reactants and we've got products, right? But what do the products then do if this is an equilibrium process? Well, they turn back into reactants. So do you see how at some level this idea of reactants and products is kind of meaningless? Because the products actually are the reactants for the reverse reaction. You know what I'm saying? We become so accustomed to having products on the right that we really don't question it. But technically, when we write Kc values, it really is right divided by left, but we call the right the products. Now guys, what if we were to switch these? Whatever's over here and whatever's over here, what would happen if we were to just write the reaction flipped? What would that do to the value of Kc? It would become the inverse of it. So guys, if you flip the reaction around, the Kc value becomes 1 over Kc because you're flipping the fraction, so you're flipping the value of Kc. We will do that experimentally later, so if that doesn't make a ton of sense, you may want to write it down, but that's fundamentally the idea. Okay, so guys, some big ideas here. So if Kc is big, the reaction favors products. If the Kc is small, less than 1, it favors reactants. If we flip the reaction around, it's 1 over Kc. And then guys, finally and importantly, Kc cannot be negative because you can't have negative molarities and you can't have negative pressures. You all good? Okay. Guys, this is important. What we're about to talk about is important. You're going to see, we're going to talk about it. It's going to make a bunch of sense. But guys, don't forget what we're about to discuss because many times this will sneak up on you and it'll get you in trouble. This is worth writing down. So guys, it goes like this. When we write Kc expressions, you're going to find out that there's 2 different types of equilibria, and this doesn't mean molarity and pressure. It's bigger than that. Guys, we have homogeneous and heterogeneous equilibria. Don't try to connect this with homo and heterogeneous catalysts. It's not related, other than that homo means all the same and hetero means different. But guys, because the definitions are the same, we can still talk about them similarly. So if we have a homogeneous equilibria, all the substances are in the same phase. An example of this is the Haber process, which we looked at previously, which is nitrogen and hydrogen forming ammonia. By the way, guys, did I mention to you that you need to know what the Haber process is? It's the only named reaction that they expect you to know in AP. I don't know why they chose it. So it's literally just nitrogen plus hydrogen making ammonia, but you do need to know it. Just a second, Spencer. So this is a 3 and this is a 2. And go ahead. What was that? No. So we had other sources of ammonia. The problem is that we couldn't make it cheaply on an industrial scale. The reason actually is because this equilibrium lies hugely to the left. So when you put nitrogen and hydrogen together, it doesn't naturally want to turn into ammonia. And that's what Haber did, is figured out a way to tweak this reaction so it shifts the equilibrium to the right. What's that? How did he do it? There's actually a blue section in our book where it talks about it. It's in chapter 15 and you can look it up. So guys, if this is homogeneous, now let's go here and talk about heterogeneous. So guys, heterogeneous obviously involves substances that are in different phases. Yeah. Maybe. So how about if we write the Kc expression for this precipitation reaction? Yeah, please do this. Guys, please write the balanced equation and then the Kc expression for this heterogeneous precipitation reaction. He's a genius. I tell you what, the segue was beautiful. So guys, now that you've had a couple seconds to start, what if you're stuck? And guys, this is something that we're going to talk about increasingly for the rest of the year. This is a survival skill that you need to learn as you're preparing for the AP test. Guys, understand that every single free response question that you sit down to on that test in May, your first response is going to be to panic and run away. It's really that kind of test. So guys, when you get into something like this, and if you don't know where to begin, what you've got to do is begin to develop strategies that allow you to get past that writer's block and give you a place to begin. And guys, sometimes that simple place to begin can be to just write down the reactants. But the trick is do something. Because right now, if you look at this and you're like, I don't know where to start, so I'm not going to start, guys, understand that those are actually habits that you're imprinting in your brain that are going to cause you to fall back to that when you sit down to the test in May. So guys, don't allow yourself to not do something. Even if it's just write down the reactants, do something. And what your something is will be different for many of you. But guys, don't let yourself now fall into this trap of doing nothing, because that's what you're going to fall back on when you sit down to the test in May. So let's do some. Are you guys done? By the way, did you get all the way to the Kc value? You're okay? Okay, so let's do this. So guys, we've got potassium iodide and lead nitrate, and I'm going to do this on another clean screen. So we've got Ki, and we've got, was it lead 2 or lead 3 nitrate? Lead 2. So we've got PbNO3, 2. And so guys, looking at this, we know that this is a double displacement reaction. Potassium is +1, nitrate is -1. So one of our products then is KNO3, and then lead is +2, iodine is -1. So our other product then would be PbI2. Is that okay? By the way, guys, how are you supposed to know those charges if you don't have our super elaborate periodic table? Well, most of the charges that they expect you to know will simply be indicated by the group. So guys, potassium is group 1. It's got 1 electron to lose, so it's +1. Iodine is group 7. It's a halogen, so it's going to gain 1. So we got those. But how do we know lead and nitrate? Well, guys, we know nitrate because you need to know the fundamental polyatomics. I know that I gave you a pass on this when we came back after the summer. You were supposed to sit this big elaborate quiz where you memorize the polyatomics and the solubilities. And guys, I gave you a pass on that. Understand that that pass was related to COVID and not related to what you're going to see on the test. So as we start reviewing for the test, you're going to need to start reconnecting with solubilities and the polyatomic ions, because nitrate, they fully expect you to just know that it's -1. Then guys, from that, we can determine that lead is +2, because if nitrate's -1, that's got to be +2 to balance. And we can take that logic and then come up with the products. Is that okay? Then we need to balance this dude. 1 and 1, oh, that's a 2. Is that it? I think that's so 2 Ks, 2 Ks, 2 Is, 2 Is, 1 Pb, 1, 2 NO. Yep, so that's balanced. Yeah. Yes, thank you. Yeah, thanks. Yeah, great point. That this does go the other direction. Thank you. You guys good? All right, so now let's do the Kc expression. So guys, it goes like this. We've got products on the right, and that would be KNO3, and that is squared. Do you see that, the squared there? We haven't done this. We talked about it, but do you see how that works? Exponent, coefficient. Okay, and then we've got PbI2, and then guys, in the denominator we've got Ki, and that dude is squared, and then PbNO3, 2, like so. You guys good? Does that sit okay? Okay, because guys, this is completely wrong. This is not the Kc expression for this reaction. It's not even close. So we need to talk about why it's not even close, which excites me because it's my opportunity to draw a beaker. You remember how much I like drawing beakers, right? So let's do this. So guys, inside this beaker, let's put everything together as our reactants. So I'm not going to worry about number, I'm just going to worry about type. So we've got K, we've got I, we've got Pb, and we've got nitrate. So guys, as reactants, we've got these things in solution because all of these are soluble. But when we then turn this into products, guys, these are not our products. If these were also our products, then we'd have no reaction. So guys, what's different about our products? And Chandler sort of led us into this. Guys, what's different about one of our products? It's a precipitate. It's a solid. Guys, which one? Is it the potassium nitrate or is it the lead 2 iodide? How about this? It's not the potassium nitrate. How do I know that? Guys, I know that because I know all nitrates are soluble in water. All nitrates are soluble in water. And all potassium-containing salts are soluble in water. Here's a concept. Those are spectators. They are always spectators. Those are, again, things that we're going to need to revisit as we're thinking about studying for the AP test. But guys, the potassium nitrate stays in solution. Those are spectators. The lead 2 iodide does not. Guys, the lead 2 iodide actually comes out. Remember how we draw solids on the AP test? We draw them in a pile at the bottom of the beaker. The lead 2 iodide does not remain in solution. It becomes a precipitate. How does that change the value for Kc? Say it again. Nope. Nope. What's it do? Let's try this. What do the brackets mean? Concentration, molarity, concentration. Do you see it now? Guys, what is the concentration of a solid sitting at the bottom of the beaker? It's not just zero, it is nonsensical. Guys, it doesn't make sense to even talk about the concentration of a solid precipitate. It doesn't have a concentration because none of it is dissolved in the water, because all of it is out of solution, precipitated at the bottom. And so consequently, guys, it's not even zero. Imagine if it was zero. It would actually cause the Kc value to also become zero. But guys, we don't deal with it that way. What we actually do is we completely remove it from the Kc expression. So guys, this is actually the Kc expression. It would be potassium nitrate squared, potassium iodide and lead 2 nitrate, well, squared, and then the other. But guys, we never include a factor in a Kc expression for a solid, because solids by definition are not dissolved in the solution. Does that make sense? So guys, you're going to find out that this becomes hugely important as we start looking at Kc expressions, because this not only happens with solids, it also happens with liquids. Guys, imagine that we were doing this. So we've got hydrogen gas plus oxygen gas, and that produces liquid water. So we've got a 2 and we've got a 2. And if we wanted to write the Kp expression for this, we might do something like this. Oh, let me do that over. So guys, we might do something like this, and we might go the pressure of the water, and that would be squared, divided by the pressure of the H2, and that would be squared times the pressure of the O2. But guys, again, this is nonsensical. Why? Because water doesn't have a pressure. This is liquid water. And guys, liquid water is a liquid and not a gas, not even vapor pressure, because that would be a vapor. Guys, liquid water doesn't have a pressure because it's a liquid. And as a result, it does not belong in the expression. So the Kp for this is literally inverse pressure of hydrogen squared times the inverse pressure of oxygen. Do you see how that works? So guys, fundamentally then, this is the summary of what we just talked about. When we write Kc expressions, we never include factors for pure solids or pure liquids. They don't have concentrations, they don't have partial pressures, and as a result, they don't get included in the Kc expressions or the Kp. They never get included. Again, if you want further explanation, guys, the idea is that while they're needed to reach equilibrium, their concentrations or pressures don't change, they don't exist, and as a result, we don't include them in the expressions. Now, guys, understand that when you get probably to your junior year in chemistry, when you're taking P-Chem, your professors then will do a much more thorough job of explaining to you why these don't show up. For us, it's comfortable and okay to just think that they don't have pressures and they don't have molarities. It is a little more complicated than that. We'll let you worry about that when you're a junior and deep into your chemistry major. It's good enough for us right now. Okay, so guys, you good on that? Yeah.
We still don't use pure liquids in KC.
You do not. No. So if you had a reaction that created, and I'm struggling to come up with an example, but if you had a reaction that created a liquid that wasn't then dissolved in water, it doesn't have a molarity. It would actually separate out as another layer. They would be physically distinct. You would have the aqueous portion of this. This happens all the time in organic chemistry, where you produce like alcohols and oils and things like that. Well, alcohols dissolve. We'll talk about oils. So a lot of times you'll do reactions that'll create oils that don't dissolve in water, and those would not show up in a KC because they're not dissolved in water. Yes, but then understand it wouldn't be the substance. It would be broken apart into things, and it would be in water. And even if it was organic, so if it was a non-electrolyte, it's still dissolved in water, so it's separated. It's broken apart from each other, and we would include it then. What else, y'all? You guys good? Yeah? No, absolutely. Yeah, so understand that this is a bullet we can't continue to dodge. You won't see this relative to liquids. Like it would tell you in the reaction gas, gas, liquid, like I showed you a second ago. But they do expect you to know some of the fundamental solubility rules. They don't get super nitpicky. You may remember at the beginning of the year, we summarized table 4 point something or other. And we just came up with some generic summaries. All the halogens dissolve in water unless they're bonded to silver, lead, or mercury. That all the group 1 and group 2 metals form soluble. Those are the general things that you need to know. And we'll talk more about it as we talk more about the AP test. So, you guys good? Okay, one more thing to do and we're done. You ready? This is based again on KC expressions. And guys, these things are called reaction quotients. You'll find out in a minute they are abbreviated Q. And you need to understand reaction quotients in a predictive sense. So guys, let's do this. Let me just lay this stuff before you, and then we're going to grab our tubes and we're going to talk about what this means. So guys, a reaction quotient is a way of using Q values to make predictions about the way reactions will proceed. And guys, it's critical that you understand this is about reactions preceding and not what they do when they're at equilibrium. I know that this is early and you don't fully understand what we're talking about, but guys, fundamentally it's the difference between an equilibrium lying to the right and an equilibrium moving to the right. And we'll talk more about that as we go. And again, I know that you'll understand this once I show you the blue tubes. For now, just bear with me. So guys, in order to do this, what we do is we plug in what are called instantaneous concentrations into a KC value. And when we do this, it's no longer KC, it's termed Q, which is a reaction quotient. Now guys, this is going to seem weird, and again, I know you're not understanding this, just get it in your notes and all of a sudden it's going to make sense. Guys, Q and KC are equal only when a reaction is at equilibrium. At any other time, the relationship between Q and KC lets us figure out what direction a reaction will proceed. That's the value of Q, is it allows us to make predictions about the direction reactions are going to go. This is going to be hugely important when we start building batteries at the end of March. Knowing the Q value for a battery will actually tell you whether it's dead or not. And we'll get into that later. You guys okay? Let me get in blue water position. You guys okay? Okay, so do you guys remember the numbers? When did this settle down to equilibrium? Do you remember the volumes? 65, 35? Okay, thank you. All right, so guys, this is probably worth writing down. So we've got Kc for this reaction is concentration of products divided by concentration of reactants, and we've got 65 milliliters, not really a concentration unit, but it's representative of concentration, and then 35 milliliters like so. So that's equilibrium, right? So I'm just going to cheat and get there just by pouring. Okay, so there's 65. And, oh, wait, still need that. And 35. That's good. Okay, so guys, this is now at equilibrium. Now what we're going to do is, and let's make sure we're clear. This 65-35 ratio is at equilibrium, right? And we can do this forever, and it's never going to change. It's going to say 65-35, right? Okay, now what we're going to do is this. We are now going to talk about Q. Again, worth writing down. And guys, Q is also products divided by reactants. It's exactly the same setup as a Kc expression. The difference is this. We are now going to plug in values that are not at equilibrium. Now guys, to make this easier, what is 65 divided by 35? Did you see who did that? I thought you just came up with that off the top of your head. I'm like, dang. I can't. So 13, can we just call it 2? So if there was one more seventh, it would be 2, right? All right. Let's 13 sevenths. We're going to call that 2. Okay? Now, guys, let's do this. Let's take some of our... Hold on, let me think through this. Let's do this. Let's take some of our reactant and pour it in here. And let's use easy numbers so that we don't have to push Ronnie's mathematical chops. 80-20. I know. It's a stretch, I know. So guys, what we've done now, did I do that right? Products, yeah. So now we've got 80-20. You writing it down with me? This one I can do. 80 by 20 is 4, right? So guys, here's what now has happened. Q is bigger than Kc. Yes? Here's the question. When I start doing the flippy dippy, which direction is going to be the movement of blue water? Just tell me right now, point. Which direction is the blue water going to go? It's going to go this way, right? And we can show that as this reaction now goes, we are going to have more product turning into reactant than we do reactant turning into product. And eventually, guys, where's this going to stop? Back at 65-35, right? So let me do a couple more to get it back to 65-35. And let's just say that I'm there. I think I'm pretty close. So guys, in fact, you did see, though, that this went down and this went up, right? So the reaction moved towards reactants. The reaction moved to the left. So guys, that is always what will happen, is this will always shift toward reactants, or we could say shift to the left. So guys, anytime Q is greater than KC, and again, that's the value of Q, is it allows us to make predictions. Anytime Q is greater than KC, I got you. Anytime Q is greater than KC, the reaction, in order to get back to equilibrium, is going to shift to the left and it's going to make more reactants. Now guys, how on stinking earth are you going to remember that when you don't have blue tubes and you're just given two numbers, 4 and 2, and you're like, oh my gosh, okay, which direction is this going to go? Guys, how do you make sense of this logically? What can we hang on to that we can remember that says if Q is bigger than KC, the reaction is going to make more reactant and shift to the left? That's true, but how can you simply remember that in order to get back to equilibrium, this requires a shift towards making more reactant? You could just memorize it. I don't memorize well at all. At this? Okay. Yes. That's exactly the way I think of it as well. So guys, if you've come up with another way that you like to think about this, that's fine, and I know this is short notice, but the easiest way that I've found to keep this straight is I simply ask myself, which one do I have too much of? Let me say that again. Which one do I have too much of? So for example, if I know that this is 2, which is functionally 2 divided by 1, right? Well, if I've got 4, which is functionally 4 divided by 1, I know that I've got too much of what's in the numerator. And what's in the numerator is product. So I now know that I've got too much product. So in order, Ronnie, as you said, to get back to equilibrium, I've got to get rid of the extra product, which means the reaction is going to turn it into reactant and it's going to shift to the left. Does that logic make sense? That's the way I think of it as well. Go ahead, Soph. Yeah, let's do this again. So here's the idea. So we established this equilibrium, and I'm going to just get close. We established this mixture that was at 80-40 or at 80-20. It's no longer at 65-35. So the idea is that when we do this math, products divided by reactants, 80 and 20, that's 4. And 4 is bigger than 2. We know that equilibrium lies at 2. We've now created a situation where we've got 4. That in order for that to be the case, that means we've got too much numerator. We've got too much product. So to get rid of this, and as Ronnie said, get back to equilibrium, the amount of product has got to go down, the amount of reactant has got to go up. And the way that that happens is product turning into reactant, which shifts the equilibrium to the left. Is that okay? Do you guys want a minute to scratch that down? Or are we? Let's just pause for a second and stew on that. You okay? So guys, would it be helpful to you if I showed you the opposite example where Q was below KC and we could then think that the equilibrium would make more product? Do you want to see that? Or can we just assume, should we do it? Okay, so let's do this. Let's set up a Q of 1. So 50-50. So here we have a Q, there we go. So guys, now we have a Q of 1, which means we've got products divided by reactants, 50 divided by 50 is 1. And now as this reaction takes place, which direction's the flow going to go? That way, because we need more product and less reactant. So right now, guys, think about it this way, back to, oh, hey. Could we do this in 2 minutes? Uh-oh. Where at? Okay. So the last time we had mercury in the school, they about shut the place down. I need to be careful what I say because I'm recording. So I can take it from you. Do you have it with you?
Yeah. It's in there.
Let me just have it.
So sorry.
No. Let's do this. Let me hang on to this, and then can you come back third period?
Yeah.
And can we talk?
Yeah.
Okay. You should be aware of this situation. We'll talk. No. I told you about what happened. And the guy came in, the woman came in, freaked out, wanted to shut the school down. They brought in the hazmat guy to pick up the mercury from me, and he was like in coveralls and a t-shirt. Completely, anyway. I've said enough. We'll talk more when we're not recording. Okay, so guys, 50-50, right? Back to the concept. Guys, we're at 50-50, and this is the way I think about it. Which one do I have too much of? If my fraction is now smaller than KC, my fraction is now 50-50. So if my fraction is, think about it this way. If my fraction is too small, do I have too much numerator or too much denominator? Too much denominator. I've got too big a number in the bottom of the fraction. It's making my fraction too small, which means I've got too much denominator, which means I've got too much reactant. So what's the reaction going to do to get rid of denominator? Well, it's going to turn it into product, and we're going to now be moving the reactant over to product. And guys, be careful about the way we talk about this. We don't say the reaction favors products. We say the reaction is moving towards products. Do you see the difference? We already know the reaction favors products because Q is greater than 1, or Kc is greater than 1. So that tells us the reaction favors products. Q being less than Kc tells us that it will move towards products, getting back to equilibrium. Go ahead. Yeah, so typically this question about Q is this really random question that they throw at the end of the entire thing. So they'll give you an equilibrium process, and they'll say, well, I can't even talk with you yet about what some of the things they'll have you do, but they'll say, here's the reaction, write the Kc value. Products divided by reactants, be careful for solids and liquids, You write the Kc value. Then they'll say, solve for Kc, and then you come up with Kc. Then they'll say, under these unique circumstances, what would the concentration of this be? Then you use Kc and solve for that. And then at the very end of the thing, they'll say, you run this reaction another time, and this time, the initial concentrations are these. Calculate Q and figure out from that, not their words, figure out from that the direction the reaction will proceed to come to equilibrium. You see how that fits together? Okay. Guys, what else? Other things you want to talk about relative to Q? You're all done? Okay. So, guys, while we are done, we are not finished. We very purposefully, this is not an accident, guys, we now have about 20 minutes left. And guys, we have, so you've already seen this, right? You already saw the you already saw the homework? We're good? Okay. All right. So guys, for the next 20 minutes, what I'd like to do is talk with you about the AP test. So, guys, the last thing that I want to do here is dwell on the past. But I want to explain to you where this conversation is coming from. So, guys, typically at this point in the year, AP classes, and I'm not just talking about this class, your AP teachers meet together. We talk frequently. And we are all beginning to see some things within our AP populations that we haven't seen before. And so we're trying to figure out how to best address these things. You may have noticed that I've been having conversations with some of you as individuals, trying to get a sort of my thumb on the sort of the what's going on out there. Anyway, guys, the bottom line is this. Every year, this week, I come before my AP classes and I'm like, okay guys, we're gonna covenant together. We're gonna sign a contract. It's time to put up or shut up. Are you going to take the AP test? And everybody says yes. And then we say, do you understand the amount of work that it's going to take to pass the AP test? And most people go yes. And then we clearly define what that work is. And then guys, it really becomes this rallying point where we all come together almost like a volleyball team before state, where we're like, we want to crush Mountain View at state. Here's what we need to do over the next 3 or 4 weeks in order to get there. Ready, set, go. And all of a sudden this AP test becomes this common enemy that we're all fighting against, and it just defines everything that we do for the next 2 months. Guys, I'm beginning to suspect that approach to the next 2 months will not be as unifying and as effective given the realities of where you are personally, socially, nutritionally. It's different. So guys, I was actually talking with Natalie, is it Gelfi? Psych teacher. I forget, is it Gelfi now? Is that her married name? Okay. Anyway, I was talking with her about this the other day, and she said something really brilliant that I'd like to share with you. She said, the thing that I'm noticing in my AP classes, this is her speaking. She said, the thing that I'm noticing in my AP classes is that my students are losing sight of their why. And I was like, dang, girl, you're bright. But I was like, tell me more about what you're thinking. And she said, normally at this point in the year, the why has changed. That typically, guys, in my class, why are you taking AP? I want to be a doctor. I want to be a chemist. I want to be this. I want to be that. I know that I need this class to be successful in college. But guys, after the poop storm that has been the last 9 months, frankly, some of us are losing sight of our why, and she's seeing that in her class as well. So typically at this point in the year, we change what our why is, and the why is the AP test, and it's like game on in 2 months, and we're going to kick butt, and we're going to nail the AP test. And she was like, I don't know that students still share that why. So guys, what I'd like to do is this. I would like to respectfully, but honestly, give you the opportunity to identify your why. And based upon identifying your why, you are then going to make some commitments relative to what the rest of the year for you is going to look like. With that said, guys, if I may, what I don't want to do is I don't want to tell you what your why should be, but I would like you to have the opportunity to rub a crystal ball and look into the future. Because guys, I know right now it's hard to think about next week, let alone next fall. Allow me, if you would, to give you a glimpse into next year. Because every year I get emails like this. I get emails from students, typically that are freshmen in college, that are going, thank you, thank you, thank you. And guys, I understand this is really the case. You have absolutely no idea how crazy your freshman year in college is going to be. It's awesome and it's fun and it's amazing, and you're going to look back and you're going to be like, that was the best year of my life. But guys, there are also parts of it that are like, oh my gosh, I had no idea what I was capable of. And as you get into the middle of that, you start thinking about the people that helped you be successful and the experiences that helped you be successful. And then you start writing emails like this. This was actually 2 years ago. Last year I didn't get as many of these emails because by BYU. My kids were also in quarantine, and they were in survival mode. So this landed spring of 19. It says, hey, Mr. Knapberger, I hope this year with your AP students is going well, and more generally that you're doing well. I thought you might enjoy a quick update, and I do, on my chemistry-related life, especially because my success is due in large part to my experience in AP Chem and Lab. Last semester in Gen Chem 1, this particular student is up at the U. I did super well. I got 100% on both a quiz and a midterm, and on my final I got a 98. Not bad. That'll work. The class itself was for the most part super easy, even boring for me, because I'd gone through the difficult task of learning how to study and learning the material from you. Guys, please separate those ideas of learning to study and learning the material. Moving on, it says, on a few occasions, my chem professor explained some of the material in a manner that was way more confusing than when you taught me the material. This semester, I decided to take Gen Chem 2 online. This was not last spring, it was the year before, so that I could go at my own pace and get done before the semester is over. I wouldn't have been able to do that if it weren't for my preparation and background knowledge from AP. I took Gen Chem Lab 1, and it was pretty easy class for me because I'd already done many of the experiments before. She lists what those were. We did so much titration. Tell your AP kids to get really good at titrating. It really is so much fun. I wasn't able to use my lab notebook from AP for Gen Chem 2 credit because I want to go to medical school, but having lab background from AP really helped me do a good job in Chem Lab while being able to focus most of my time towards other classes. Thank you so much for making us work hard to prepare for the exam. Learning how to study both efficiently and effectively has been really beneficial to my success. So again, we're rubbing the crystal ball a little bit, right? Because I wanted to give you the opportunity to rub the crystal ball. So now that we're done rubbing the crystal ball, guys, this is what I'm about to hand to you. So I really want to know your answer to this question. What are your aspirations for the rest of the year? And in speaking with some of you, I tried to summarize generally what I was hearing into 3 specific groups. Some of you are thinking this: I'm not concerned about the AP test, but I do want to develop a deep understanding of course material while learning to prepare for comprehensive exams, knowing this will benefit me in the future. Now, guys, understand, I know you're reading ahead, but hear me out. So these are the people right now that are going, I know that I need to know this material in the future. I know that I've got to get this, but I may go take the AP test. I'm not sure. But whether it's AP Chem or not, I know that I'm going to come out of Orem High School having no clue how to study for comprehensive finals. You guys understand that, right? The only classes that you take at Orem High that look anything like finals week in college are your AP classes. No matter what we say about finals week at the end of the year, it's not. Anyway. That number two is that I am motivated to pass the AP test by developing a deep understanding of course material while also learning to prepare for comprehensive exams. And then guys, finally this last one. I'm not concerned about the AP test and plan to ride out the rest of the year fulfilling the requirements of the course, but not investing additional time and energy in truly mastering material or learning to prepare for comprehensive exams. So guys, fundamentally, it comes down to this. I'm not really caught up in needing to really understand the course content deeply, but I see the value in learning to study for comprehensive exams. Here, I want to be ready for the AP test, and I understand that to do that, I need to do some work, which will then help you experience how to study for comprehensive exams. And then guys, down here is just you looking into your soul and going, you know what, I'm done. I've done what I can. I'm ready to just cut my losses. I'll figure out how to study for comprehensive exams in college. I'm not worried about passing the AP test in chemistry. I'm just going to keep coming to class, keep doing homework, keep taking tests. I'm going to treat this as an isolated class and not a class that's preparing me for AP tests or studying for comprehensive exams. I'm just going to finish the year and be done. Now, guys, understand, strangely, that doesn't mean you're not taking the AP test, right? Because if you want to walk into the AP test cold and see how it goes, that's totally fine with me. Guys, understand, I don't in any way, I'm not worried about my pass percentages. So if you want to just go, you know what, I'm done, but I'm going to go take the AP test just because, that's totally up to you. I don't have a problem. You're not betraying me if you choose to do that. Because I think that generally you can fit yourself into one of these three groups. Now understand that your reasoning may be more nuanced. It may be, you know what, I know that when I get to college I'm not going to take my AP Chem credit, and I'd really love to pass my English test because I really don't want to take English in college. You guys understand there's a name for that. It's Cody. That's what my son did. He still passed he would have passed the chem test had they not lost his submissions. But guys, understand that that's totally legitimate. If you're just like, I know that my time could be better spent doing other tests, that's great. But you may still want to consider whether it's worth still engaging in the review process, simply because you're going to need to know the material later and you're going to want to learn how to study for big exams. So, guys, if you don't feel like you fit cleanly into a category, I'd love for you to flip the paper over and write a greater explanation of where you're at, but I am going to ask you to commit. Yeah.
You're still usually advised to not take the credit even if you pass it or going to continue.
Yeah, so Donnie's question is, are you still advised to not take the credit? And understand, there are teachers, AP teachers at Orem High School, that believe that what I'm about to share with you is bordering on blasphemy. But there are teachers here that I respect hugely that vigorously disagree. But this is my 2 cents. If you know that you're going to need chemistry long-term in whatever it is that you're going to do, don't get out of taking freshman chem based on your AP scores. Every year I have a couple students that do that, and without exception they come back and they say, I wish I'd listened, because all you're doing is moving into honors freshman chemistry, and it's tough. I mean, understand, you're trying to figure out how to live on ramen noodles and how to not kill your roommates, right? That's bad enough, not having to do honors chem. So guys, this is what I'm going to ask you to do. I would suggest that if you fit into category 1 or category 2, whether you're worried about course material or whether you're just worried about how to review for big tests, you want to commit to engaging in the review process. And guys, this is what this looks like. You are committing to 2 hours a week. In addition to the homework and the chapter summaries and everything else, the normal stuff, you are going to add at least 2 hours a week to going back and relearning all the material that we have learned this year. To do that, I'm going to give you AP review books in just a minute. So guys, every week, starting next week, you will be going through these books and you are committing to read, review, and relearn all of this material and answer the questions at the end of the chapters. Now guys, understand, this number used to be 4. Listening to some of you, I've heard you say, I'm busier than I ever thought I would be, even though school is short and we don't have school Wednesday. Because I don't know what to attribute that to, but I am trying to learn from my audience. I think if I had put the number 4 there, which frankly is a more legitimate number, about an hour a day, because I think that some of you would have just been like, no. So compromising a little bit, 2 hours, not enough, but it's a good start. Then guys, in addition to that, the other things that you're committing to is this. When class is done, somewhere around spring break, when class is done, Once we no longer, can you imagine? Once we no longer have homework and chapter summaries and tests and things like that, we are then going to move up to 4 hours per week. But that is actually a reduction in your total workload because you won't have homework and chapter summaries to do anymore. Then guys, in addition to that, you're also committing to take all the practice exams. All that happens in class, and then also invest the time out of class to identify your weaknesses and figure out what you need to do personally to address these. So guys, this is what it looks like to get ready for comprehensive exams. Whether you're planning on taking the test or not, if you would like to engage in that, that's great. But guys, do understand this. If you say yes, it becomes a part of your grade. There will be assignments under the same assignment category as your chapter summaries. And every week, you are simply going to say yes or no. And the question is, did you do your hours? And if the answer is yes, it's 10. And if the answer is no, it's 0. And there's no way to make them up. Because guys, understand the idea here is doing these late is breaking the underlying reasoning behind this, which is consistency over time. So you don't make them up. Understand that if you choose not to engage in this review process, those will just be excused. What that means then is that your grade for fourth quarter and partially third quarter is just going to be based on fewer project assignments, which means that your chapter summaries are going to become even more important to do on time. So, guys, that's it. Questions, thoughts, things that you want to share relative to this? You okay? Okay. No, understand that what it means is that you are not actively engaging in the review process. You shouldn't expect to do well on the AP test, but if you're comfortable with that and you're just ready to walk into this thing cold and see how it goes, yeah, Spencer, that's completely up to you. So, guys, the only time that I've ever seen this backfire was one year where I had a kid tell me no, he wasn't going to do the review work. Well, I guess it's kind of this is a weird year. He told me no, didn't do any of the review work, and then went and took the test anyway. But I'm offering, you need 2 of those. I'm offering that to you guys as well. So guys, you need 2 of these. And guys, understand, I would love to sit and talk with you if you would like to dig into this more deeply. No. Okay, so guys, you need 2 of these. One of these you are going to return to me next week. Hold on a second. Guys, one of these you're going to return to me next week. The other one you are going to keep because you need the review schedule. Kaylee, I know you need to go. Here's your review book. Put your name in it because they all look the same. Guys, for the rest of you, we're going to take a couple minutes because I want to get these books in your hands. And then, guys, we will take a break. We'll just do it on our own schedule. Sorry. Do you want to hand those down? Is somebody gone? Oh, yes. Ellie's gone. I'll hang on to it. So, guys, one last thing before we take a break. Originally, the plan was that you guys were going to pay for these. But in speaking with our financial folks, we actually had money available so that I can buy them for you. So you don't owe any money for these. They have not been charged to your account. These are compliments of the AP gods. So guys, please do write your names on them. They're going to get shuffled all over the place. But guys, here's the deal. You do not need to bring these to class yet. So when this talks about chapter reviews, that is chapters out of here. Well, units out of here. So you'll find that in the front here. Guys, there's also some great information in these books about how to take the AP test. We'll talk more about that after spring break. But guys, all of the review that you are committing to do is out of this book. And then guys, after spring break, we will also use these as a resource during our in-class reviews. And guys, let me just explain that to you as well, and then we'll be done. When we're done with course material, I think that we're going to need to continue to work in lab simply because we're behind in lab, and labs are important for you being successful in college. But in lecture, we're going to be done. And then for the majority of the month of April, bleeding into May, we're going to spend second period, and we are just going to hammer on practice questions for the test. We will actually even sit a couple full exams to give you the experience of doing that. Now, guys, understand that if as a result of this commitment form, you're like, deuces, I'm out, I don't care about the test, you are still expected to be here. You're still expected to take these exams. You're still going to pretend like you're moving towards the test while you're in class. You probably won't be working outside of class, but you will in class. And if that becomes not the case, then I reserve the right to have you sit a full AP exam while your classmates are taking it for real and count it on your grade. Now you just discovered your why. Guys, with that said, I hope you understand the spirit of this entire thing. As much as you are weary, perhaps, and having a hard time seeing over the horizon, guys, your teachers are in the same place. We get where you're at, but at the same time, we also have insights into where you're going. We've been through college. We've sent thousands of kids into college and helped them be successful. And guys, regardless of what now feels like, you want that to feel good. And it may mean that you just have to dig in your heels a little bit and go, yeah, I know this isn't what I want to do right now, but it's what I need to be doing right now. But at the same time, guys, if you're just like, you know what, I just want to make this okay, and then I'll worry about that later, that's fine. But I need to know that. And you need to know that. So, guys, we're done. Anything else to chat about relative to this? You're good? Okay. So 5 minutes, come back, grab your labs. We're going to meet in here and then go next door. Go get them.